rotational counterpart to force is torque. Forces cause translational motion, whereas torque makes objects rotate. Recall that Newton's second law states that the net force acting on a body is equal to the mass times the acceleration. This is the translational version of Newton's second law. The rotational version of Newton's second law states that the net torque acting on a body, usually indicated by the Greek symbol tau, equals the product of the body's rotational inertia I times the body's angular acceleration alpha. The simplest kind of rotational problem is one in which the sum of the torques acting on a body is zero, or in other words, the angular acceleration is zero. These are called rigid body or equilibrium problems. Before we can try a problem of this type, though, we need to discuss the concept of torque. How do we calculate the torque of a system? Assume you have a stuck bolt that you want to move. You attach a wrench to the bolt and do what comes naturally. If the bolt moves and begins to angularly accelerate, what determines the angular acceleration, assuming the torque remains constant throughout the motion? The most obvious parameter involved in making the bolt move is the magnitude of the applied force. If the force you apply is small, it is less likely that you will break the bolt free than if the force is big. If the bolt does break free, a larger force will produce a larger angular acceleration. Another consideration is where you apply the force. One way of quantifying this is by defining a position vector r, which extends from the axis of rotation to the point where the force is applied. For a given force, the torque is greater when the force is applied farther from the rotation axis. You might be familiar with this concept. For example, a longer wrench gives you more leverage. In other words, the longer the distance vector r, the greater the torque. The last parameter that affects torque concerns the angle at which the force is applied. This is quantified by defining the angle theta between the line of the force vector and the line of the position vector. It is intuitive that an angle theta of 90 degrees yields the largest torque, whereas a theta of 0 or 180 degrees would produce no torque, and the bolt would not turn. For an arbitrary force direction, let's break the force vector into two component vectors, one parallel to the distance vector r and another perpendicular to r. You can probably see that the parallel component of force, which equals F times cosine theta, will not make the bolt rotate about its axis, but the perpendicular component of force, F times sine theta, will. Now let's write down everything we know about torque. The important factors are, first, the size of the force, second, the distance from the rotational axis to the point at which the force acts, and third, the angle between the force and the distance vector. With these, we can write a compact mathematical equation for torque equal to r times the force times sine theta. The units of torque are Newton meters. The product of r times sine theta is sometimes called the moment arm and is denoted as r perp. Thus, the torque can be written as the force times the moment arm. Torque can also be written in vector form as equal to the cross product of the line of r and the force vector. Recall from the properties of cross products that the magnitude of torque is r times F times sine theta, which is what we had before. For the different situations shown here, if the magnitude of the force that acts in each case is the same, which one results in the largest torque? Correct. Let's go through an example and calculate the torque acting on a falling meter stick with one end fixed on the ground when it makes a 45-degree angle with the ground. The mass of the meter stick is 0.3 kilograms. Which force is acting on the meter stick causing it to fall? Correct. At what point on the meter stick does gravity act and which way does it point? Correct. What is the angle theta between the force of gravity and the line of r? Correct. What is the distance between the rotation axis and the point where the force acts? Correct. What is the equation for torque? Try again. Correct. What is the torque acting on the stick? Correct. Let's now consider a statics problem where a beam of length L has one end attached to a wall and is held in place by a cable connected to the other end of the beam. If the beam makes an angle theta with the wall, what is the tension in the cable? The first thing to consider is that the beam is not moving, so we are dealing with an equilibrium problem. This means that the acceleration, or if rotation is involved, the angular acceleration, is zero. In this case, if the cable were suddenly cut, the beam would fall. Since the beam is connected to the wall, it would rotate around the connection point. Thus, with the cable in place, the angular acceleration is zero, which means that the sum of the torques is zero. What two forces acting on the beam produce torque? Correct. What is the torque acting on the beam about the rotation point that comes from gravity? Correct. What is the torque acting on the beam about the rotation point that comes from the cable? Try again. Correct. Now that we have the individual torques, which equation best describes the sum of the torques? Correct. If the beam has a mass of 3 kilograms and the angle theta is 30 degrees, what is the numerical value of the tension? Correct.